Welcome to the second video on geometric progression. This is another 10 questions. Let's start doing them. The probability of success is 0.2 here. So probability of 3 is 0.8 power 3 minus 1, 0.2 power 1. That should give me 0.128. Between 3 and 5, so plus 3, 4, and 5. I'll have to add all of them up. There's no other choice. So 0.8 power. So that's 1.128. Let's just write 0.128, 0.8 power 4 minus 1, zero point 0.2 power 1 plus 0.8 power 5 minus 1, 0.2 power 1. Greater than 4 has the formula 1 minus q power, q power r minus 1, q power r, or q power r minus 1. Q power r, so I get 0.8 power 4. You have to remember your formulas in this case. Most of these questions will rely on your ability to write down the correct formula. 0.4096. Two independent values of x are found. Find the probability that the total of these two values is 3. So 3 can come up with 1 and 2, or 2 and 1. You cannot have 3 and 0. Why? Because geometric does not have 3 and 0. So this becomes 0.8 power 1 minus 1.2 power 1 into 0.8 power 2 minus 1 into 0.2 power 1 plus 0.8 power 2 minus 1 into 0.2 power 1 into 0.8 power 1 minus 1.2 power 1. I think that should give me the correct answer. Yes, they together give me 0.064. Moving on to question number 2, the diagram shows part of the distribution of the discrete random variables v, w, x, y, and z. One of these variables has a geometric distribution too. State with the reason which variable it is. Now for geometric distribution to have to be here, the mode should be 1, so the highest probability should be 1. So it can't be this, it can't be that, it can't be that, it can't be that. This could be the case, but in this case there's a 0 as well, so this can't be another geometric distribution. So in this case, none of these distributions are geometric. Therefore, we're going to say that none. One of these distributions has a distribution 4 comma half of a binomial. State with the reason which variable this is. So it has to have 4 trials, and the probability of success is half, so it should be more or less symmetric. Okay, that is what half gives you, and the mean should be at 2, and the median should also be at 2, and all of those things. So I think this one would fit uh, into the binomial. So when you have probability of success is half, the distribution comes out symmetric, which is the case for most coins when they are tossed if they are not biased coins. Okay. Moving on to question 3, 60% of the voters at a certain polling station are women. When voters enter the polling station one at a time, the number of voters who enter up to and including the first woman is denoted by X. State a suitable distribution that can be used as a model for X, given the values of any parameters. Okay, first woman. So that tells me that I am looking at the geometric and my probability of success is 0.6. So yeah, the second thing that I have to tell you is that trials should be independent. And success is the same, so each voter should have the same probability. So 4 0.4 power 4 minus 1, 0.6 power 1. That gives me 0.0384. Probability of x greater than or equals to 4 is q power r minus 1. So I have point 0.064. Question 3. Question 4. A clock is designed to chime once each hour. On the hour, the clock has a fault, so that each time it is supposed to chime, there's a constant probability of 1/10 that it will not chime. It may be assumed that the clock never stops and the fault occurs independently. So I am looking at a geometric distribution. The clock is started at 5 minutes past midnight. So I'm starting at 0005. On a certain day, find the probability that the first time it does not chime is at 6 on that day. Okay, so let's see how many times that once each hour on the hour. So I am talking about 6 o'clock. So it's the sixth time that the clock has to chime and it does not chime. So I'm going to say that for the first 5 turns, there's going to be a failure. And the last one is going to be a success. The success is that it does not chime. Okay. So zero point 0.9 power 6 minus 1 into 0.1, 0.059. Before 6 on that day. So before 6, x is less than 6. For less than 6, I have the formula 1 minus q power r minus 1. So 1 minus 0.9 power 6 minus 1. 4095. Okay, 951. Another clock is designed to chime twice each hour, on the hour and at 30 minutes past that hour. So the number of trials has increased. It's going to be chiming at more intervals now. This clock has a fault so that each time it has a probability of 0.05 that it will not chime. It may be assumed that the clock never stops and the fault occurs independently. The clock started at 5 minutes past midnight again. Find the probability that the first time it does not chime is at either 0030, so the first time, or on the third trial. So when I have or, I'm going to add the probabilities. Okay. Use the formula for the sum to infinity of a geometric progression to find the probability that the first time it does not chime is at 30 minutes past some hour. So when I did the previous part, I treated 0030 as x equals to 1. Then 0130 as x equals to 3. So the next time is 0230, that is x equals to 5. That is the fifth interval at which it's supposed to chime, but it doesn't. Okay, then 0330. Let's see if we have a pattern of a geometric progression emerging here. This was 0.05, that was the first term. Then I had 0.95 squared into 0.05 plus 0.95. This is going to be power 5 minus 1, so 4 into 0.05. So I see a pattern emerging where every subsequent term is being multiplied by 0.95 squared. So my common ratio is going to be 0.95 squared. My first term is 0.05. So sum to infinity is a over 1 minus r, 0.05 over 1 minus 0.95 squared. 0.513. Question 5. Sandra makes repeated independent attempts to hit a target. On each attempt, the probability that she succeeds is 0.1. Find the probability that the first time she succeeds is on her fifth attempt. So zero point 0.9 power 5 minus 1 into zero point 0.1 power 1. 6561. The first time she succeeds is after her fifth attempt, so x is greater than 5. That's q power r, zero point 0.9 power 5. The second time she succeeds is before her fourth attempt. So I'm now talking about two successes. So it's like the previous marathon where I had a case where I was talking about two successes. So x is less than 4 means I can have 3, I can have 2, I cannot have 1. So in the 3, the first two trials can have one success, and the third has to be a success. And the first, there are basically two successes, P into P. Okay, so that gives me to C1 0.9 power 2 minus 1 into 0.1 power 1. That's the first success in the first two turns, and then zero point 0.1 plus zero point 0.1 squared. 0.028. Okay, Jill also makes repeated attempts to hit the target. Each attempt of either Jill or Sandra is independent. Okay. Each time that Jill makes attempts to hit the target, the probability that she succeeds is zero point 0.2. Sandra and Jill will take turns attempting to hit the target, with Sandra going first. Find the probability that the first person to hit the target is Sandra on her second attempt. Uh, and Sandra going first. So Sandra was zero point 0.1 when she was hitting the target, and Sandra needs to succeed so she needs to fail once. Jill also needs to fail once, and then Sandra needs to succeed. So that's zero point 0.9 into zero point 0.8 into zero point 0.1. I can also make a tree diagram, but it's going to be a long tree diagram if I look at the second part. Okay, so 0.072. Okay, now for part B, 10th attempt. So it's going to be a long list of, 10 turns for Sandra and 9 for Jill. So let's start making that, and it's probably going to make sense once I start doing it. So zero point 0.9, Sandra fails, Jill fails, Sandra fails, Jill fails. Okay, so this is going to go on. So how many times does Sandra have to fail? 9 times. How many times does Jill have to fail? Again, 9 times. And then Sandra will succeed. So zero point 0.1. So it's zero point 0.9 power 9 into zero point 0.9 power 8, zero point 0.8 power 9 into zero point 0.1. I think that should be the correct answer. I am getting 0.0052 rounded to three significant figures. Question 6. The score when two fair-sided die are thrown in the sum of the two numbers on the upper paces so that the probability that the score is 4 is 12. So I can make a simple 1, 2, 3, 4, 5, 6 possibility diagram. 4, 4, 4. So that's 3 out of 36. That's 1 out of 12. The two dice are thrown repeatedly until a score of 4 is obtained. The number of throws taken is denoted by the random variable x. So this is a geometric progression until a score of 4 is obtained. So your success is basically 1 out of 12. So your expectation should be 1 over 1 over 12, which is 12. Find the probability that a score of 6 is obtained on the 4 is obtained on the sixth throw. So 11 over 12 power 6 minus 1, 1 over 12 power 1. Let's see if we're getting the correct answer. 0.03539. Less than 8 is 1 minus q power r minus 1. 1 minus 11 over 12 power 8 minus 1. 0.456. Okay, so that was question 6. Question 7 says a pair of coins is thrown repeatedly until a pair of tails is obtained. The random variable x denotes the number of throws required to obtain a pair of tails. Um, okay, so a pair of tails. Okay, so the probability of two tails is half into half, 1/4. So the expected value is 1 divided by 1/4. So that's 4. Find the probability that exactly 3 throws are required to obtain. So 3 throws, 3 over 4 power 3 minus 1, 1 over 4 power 1. I think that should work. 27, no, sorry, 9 divided by 16 divided by 4. 0.141. Find the probability that fewer than 6 throws. Point 763. Question 8. Kayla is competing in a throwing event. Throw is counted as a success if the distance is achieved is greater than 30 meters. The probability that Kayla will achieve a success on any throw is 0.25. Find the probability that Kayla takes more than 6 throws to achieve a success. Okay, so more than 6 throws. Q power R, 0.75 power 6. 0.178. Find the probability that for a random sample of 10 throws. Now I've told you exactly how many throws, so that's no longer a geometric distribution, it's a binomial distribution. So n is 10 and I want at least 3 throws. So I can say that this is 1 minus probability of 0, 1 and 2, 1 minus 10c 0, 0.75 power 10 minus 0, 0.25 power 0. 10c1, 0.75 power 10 minus 1, 0.25 power 1. 10c2, 0.75 power 10 minus 2, 0.25 power 2. Okay, so this calculations gives me 0.474. Okay, so the last question, an ordinary pair dice is thrown until a 6 is obtained. Find the probability that obtaining a 6 takes more than 8 throws. So that's q power r. Okay, so success is 1/6, failure is 5/6. It There's this two ordinary pair dice is run until a pair of sixes is obtained. So that's 1/6 into 1/6. That's 1 over 36. The number of throws taken is denoted by the random variable x. Find the probability expected value of x. So 1 over 36, 1 over 1 over 36. That gives me 36. Find the probability that obtaining a pair of sixes takes either 10 or 11 throws. 10 or 11. So 35 over 36 power 10 minus 1, or 1 over 36 power 1, 35 over 36 power 11 minus 1. 1 over 36 power 1. That is giving me 0.0425. That is the end of another marathon. Let me know in the comments if there are any questions, and please make sure to like, comment, and subscribe. Thank you for watching.